Hello and welcome. This is chapter number 11, AC power analysis of our Sadiku's textbook. In this lecture, we'll be talking about two important concepts. One is the instantaneous power and the second is the average power in an AC circuit. Before this lecture, we have seen how we use phasor analysis to solve AC circuits for steady state analysis. And we have also seen how we use first order and second order differential equations to solve different AC circuits. So first of all, let's start with the instantaneous power. Instantaneous power is the power in watts at a given instant of time. We can also think of instantaneous power as power absorbed by the circuit element at a specific instant of time. Conventionally, instantaneous power is denoted by lowercase letters. Also, it is the rate at which the element absorbs energy. So what exactly it means? So for example, if we have a circuit, for example, it has a resistor in it, and there is a potential difference that is available applied across this resistance and the current I that flows through the this component R, for example. And it can be R, it can be inductor, it can be a capacitor, it can be a combination of any of them. So for example, it's something like this. So for here, if say we have a V of t, a voltage across this element, so it is better to draw this as a circuit element as something like this. So we can call it as element, circuit element. So assume that we have a voltage V of t, and that V of t is given as Vm cos of omega t plus theta v, and I of t is given as Im cos of omega t plus theta I. And so the overall power for this case will be given as P of t, or as a multiple of V of t into I of t, and we just simply multiply both of them. It becomes Vm Im cos of omega t plus theta v plus cos omega t plus phi I. So this power is a function of time, and this power is basically called the instantaneous power across of this circuit, or the instantaneous power that is available across this circuit element. Instantaneous power is generally denoted by lowercase letters. So your textbook uses lowercase letters for this case. So now, say again, this is the same concept which we have talked in our last slide. So if we have a sinusoidal source and that source supplies a passive linear network, remember passive linear network, it means that the network consists of resistors, inductors, capacitors. So these are passive elements, and these are also linear elements. There are no operational amplifiers or any active elements that are involved in the circuit. So if a source is, or a sinusoidal source is connected to a passive linear network, or in an easy way RLC network, the power can be given as V of t, I of t, and say for example the voltage appearing across this is Vm cos I plus omega plus theta v, and I of t, the current through the network, is Im cos omega t phi I. The overall power can be given as this, and this power can also be written as in this fashion, and because using the identity of cos alpha plus beta, so we know that cos A and cos B is 1/2 cos alpha plus beta, so A plus B, plus cos of A minus B. So if I'm going to apply this identity on this equation, what we will get? So we will get, so I'm writing it over here, cos of, so 1/2 multiplied by cos A. So A is this, and your B is this part. So cos omega t plus theta v plus omega t plus theta I plus cos A omega t plus theta v minus omega t minus theta I. So in this case, what we get 1 by 2 cos of 2 omega t plus theta v plus theta I. First sinusoid, the second sinusoid, this omega t cancels out, cos theta v minus theta I. So this is how what we get, and this is the same relationship we are getting over here. So the important part in so now so this is basically an instantaneous power relationship, and this is a function of time. So if we are going to plot this, waveform for a time period t, where time period is 2 pi by omega, so for a time period of t, this function will look something like this, or the or the shape of the curve that is given over here. So this function looks something like this. So remember, there are two parts in it. So this part is, we can see that this is a function of time, and this portion is independent of time. This is independent of time, right? So we can also say that this is a sort of a DC component available in this power signal, and this is sort of a time function of time that is available here. Interestingly, the value of P of t can be positive, and it can be negative as well. So this is an important part. So a positive value of P of t means that your circuit is absorbing power. And with the negative part, it means that your circuit is supplying power. So if there is this passive linear network is there, and if you are measuring P of t over here, this P of t, if it is positive, it means that your passive linear network is absorbing the power. And if this P of t is negative value, it means that this passive network is source of is supplying power, or it means that there is some sort of an element that is there that is supplying power to the source, or the power is going back to the source itself. So instantaneous power, remember, instantaneous power, it is the power at a specific instant of time. We cannot say that this is the power in the whole circuit. So we have to put in the value of time. So this value of power can be calculated at this instant of time, say at this instant of time, this instant of time, this. So you have to specify as instant of time in order to measure this power. And that is why it is difficult to measure. So usually in our analysis on actual practical circuits, we are not much concerned with the instantaneous power. We are more concerned with the average power, and that is what is the power that is measured with the help of the watt meters we have in our networks. So now what exactly is average power? So average power is the average of the instantaneous power over a one time period. So we have seen that when we plot this function of instantaneous power, this function is a periodic function of time. Let's say the time period is 2 pi by omega, and this again, it's a periodic function. So it repeats itself after a certain period of time. So instantaneous power is difficult to measure, and it changes with time. So that is a precise reason which I was talking earlier as well. Average power does not depend upon time. So once we take the average power, it does not depend upon time. It gives us the average value of power in a circuit, or that is absorbed or maybe supplied by a certain circuit element. And our devices which we have, for example, watt meters, which are extensively used in the industry or in actual measurement, so they can easily measure the average power rather than measuring the instantaneous power. So average power is the average of the instantaneous power. So this is our instantaneous power. This is average power. So average power is generally given as with the capital letters, and it is integration of 1 by t or over one time period. So if I have to write it in detail, so it comes out to be something like this: 1 by 2 Vm Im cos of theta v minus theta I plus 1 by 2 cos of 2 omega t plus theta v plus theta I dt. So this is what it looks like. So if we are going to integrate it, we'll be getting our real power. So if we are going to now, let's try to integrate it. So this is the same function which I've written. So my power of instantaneous power can be given as this. So this is my instantaneous power relationship, and this is my average power. So if I'm going to integrate this instantaneous power over one time period and divided by the whole time period, I will be getting my average power. So just simply integrate it. So this first part, there is no time constant. So if I'm going to integrate it 1 by t over to t, this comes out to be something like this. Then 1 by 2 Vm 1 by t cos of 2 pi omega t plus theta v plus. So remember, this is integration of cosine over one time period. So this will turn out to be 0. So we are so this whole factor, the second term will be 0. So we are only left with this part. So if we are going to integrate it, this will be Vm Im cos of theta v minus theta I integration of time 1 by t multiplied by t minus 0. So this thing also comes out to be 1. So this comes out eventually be Vm Im cos of theta v minus theta I. This is or this can be called as our average power, and this is the same as this thing. So here, so we can say that for the average power for a circuit is given as, or can be given as this portion of the instantaneous power. So if we go and see this diagram, so this is say half Vm Im cos of omega t. So this is actually the average power, or what is the DC component which we are seeing in this instantaneous power component. This is the average power for a AC circuit, or if we are going to do power analysis for any AC circuit in such a manner, our power can be calculated by this. This is basically the magnitude of voltage, magnitude of current, and the phase difference between the voltage and the current angle or the waveforms. Similarly, this relationship. So again, remember our two relationships which we have seen earlier, Vm cos of omega t plus theta v, and I of t Im cos of omega t plus theta I. So let's do a little bit of phasor analysis of this. So I convert it into the phasor form. So V will be Vm angle of theta v. The I phasor will be written as Im angle of theta I, right? So if I'm going to find out average power in this case will be 2Vm V phasor multiplied by I phasor conjugate. So V phasor will be Vm theta m multiplied by Im. If the conjugate is this, the angle comes out to be negative. So this is, so what we get, half, if you are multiplying two phasors, the magnitudes will multiply, the angles will add up, theta m minus theta I. Oh, sorry, this is theta v, rather theta v minus theta I. So this is what we get as concept of average power. So average power is something like this. But again, if I'm going to write, so average power will be something like this. But this thing, if I'm going to if we are going to see this thing is, or if we know that r angle of theta, it is also equal to r cos of theta plus iota sine of theta. So this is the polar form and this is the complex form. So this is not exactly the average power, because remember, average power, if we are going to multiply. So average power basically is comes up with a cos of theta v minus theta I. But this part, if we are just simply doing multiplication of these two entities, this part will give us the polar form Vm Im angle of this. So this will be cos of theta v minus theta I plus iota or j sine of theta v minus theta I. So we in our average power, we have seen that we only comes up with the cosine part. So cosine is the real term, sine theta is the imaginary term. So therefore, whenever you will be seeing a power relationship, it will be the real part of the conjugate of this. So it is generally written as this. Instead of this, we are supposed to write it as P average equals to 1 by 2 real part of the value of phasors, or the multiplication of the phasors for these part. So this is basically, if we are going to multiply, we see that this is the real part. That is why this real part comes in this equation. So average power, we can always, if we are given the values in sinusoids, if we are given two sinusoids, we can just simply do the analysis and use half Vm Im cos of theta v minus theta I function. And if we are given our values in phasor forms or in phasor form, so we can always do this multiplication, and in after this multiplication, we have to only select the real part and multiply it by 2 to get our desired results for average power. So we can see from here that so generally we have two types of loads. So if we have a resistive load, so in a resistive load, our theta v and theta I are current and voltages are generally in phase, and our resistor absorbs average power all the times, right? And then we have reactive loads. So reactive loads, for reactive loads, we have the inductors and we have the capacitors, and both inductors and capacitors, they absorb zero average power all the times, because there is a 90-degree phase difference between the voltage and the current phasors. And if we have a cos of, say, just cos of plus minus 90 degrees, this value is always equal to 0. And if this value is 0, there will be no power that is absorbed, and there will be no average power that is either absorbed or supplied to the system. So that is how it goes. So so this is basically how it goes, or what exactly it happens for any circuit that have that have linear passive components, such as a resistor, inductor, and a capacitor. So for the average power is always absorbed across a resistor, whereas the inductor and capacitors do not absorb any average power. The all average power across an inductor and a capacitor is always 0. So let's solve this example. In this example 11.1, we are given a voltage signal, and we are given a current signal as well. So find the instantaneous power and the average power. So instantaneous power, P of t, is given as Vt multiplied by I of t. So just simply multiply both of them together. So 120 cos of 377 t plus 45 degrees multiplied by 10 cos of 377 t minus 10 degrees. So if you're going to multiply 120 multiply by 10 cos of 377 t plus 45 degrees cos of 377 minus 10 degrees. So using the formulas, 1200 multiply by 1 by 2 cos of a plus b. So 377 t plus 45 plus 377 t minus 10, a plus b plus cos a 377 t plus 45 minus 377 plus 10 degrees. So So what we'll get 600 cos of um, first part, say this basically cancels out each other, cos of 55 degrees plus cos of 2 multiplied by 377t plus 35 degrees. So this is our value for P of t. So from our P of t will be something like this value. Or if we are going to simplify it further, so my P of t value will be 344.2 plus 600 cos of 754t plus 35 degrees. So this is a simplified version of average power, and this average power is given in terms of watts. So always write the units watts. Right. So this is my instantaneous power. So now we have to calculate average power. So average power, remember average power is 1 by t, 0 to t, P of t dt. Also, we know that it comes out to be 1 by 2 Vm Im cos of theta v minus theta I. So if we are going to put in the values, Vm 120 multiplied by 10 cos of 45 minus or plus becomes plus 10 degrees. So if this comes out to be 1 by 2 into 1200 into cos of 55, and this value is 344.2 watts. So this is my average value. Remember, if you have calculated the P of t, this value will always be equal to the average power that is being absorbed by the circuit. So this is how we are going to solve it, or we solve this such circuits for instantaneous and average power values. So let's solve another example. In this case, we are given to the values in phasor form. So first value, we are given an impedance of 30 minus J70, and the voltage across this impedance is 120 volts. So my voltage across this impedance is 120 angle of 0, and this impedance is 30 minus J70 ohms. So the current is V by Z, just simply 120 angle of 0 divided by 30 minus J70. So the current, the value of current in amperes will be 1.567 to 1.576 angle of 66.8 degrees amperes. So this is the value of current that is appearing across here. So now with this value of current, what we'll get, we can find out average power. Average power as 1 by 2 Vm Im cos of theta v minus theta I. So we have 1 by 2, our value of Vm is 120, Im is 1.576, cos of theta v is 0 degrees minus theta I is 66.8 degrees. So if we are going to find out the values, it will be 37.24 watts. So my average power for such a circuit will be something like this. And we can solve this thing with another fashion as well. Again, we have say similar circuit. We can use the phasor analysis, which we have seen, 20 angle of 0 degrees. Our Z is 30 minus J70 ohms. My current value or the current phasor value is this. So current is 1.576 angle of 66.8 degrees amperes. Remember, average power is half times the real part of VI conjugate. So the real part, half times the real part of VI conjugate. So V is 120 angle of 0 multiplied by 1.567 angle of minus 66.8 and doing the conjugate here and taking the real part. So if I'm going to take the real part, it will be uh, again 120 into 1.576 cos of minus 66.8 degrees. And this again turns out to be 37.24 watts. Right, so this is the average power that is absorbed across this circuit. So overall, this is how these are the two methods in which we can use to find out the average power absorbed by any impedance or in a circuit and something like that. So let's solve another circuit. So in this example, it says that for a circuit shown, find the average power supplied by the source and the average power absorbed by the resistor. So in this network, we have to find out power supplied and power absorbed. So we have to find out these both values of what is exactly the power supplied and what exactly is the power that is absorbed by the source. So first of all, in this case, we know that voltage or the V source is 5 angle of 30 degrees. Our overall impedance is 4 minus j 2 ohms. So my current value is V by Z. Our current value will be 5 angle of 30 degrees divided by 4 minus j 2, and this turns out to be 1.118 angle of 56.57 degrees amperes. This is the value of current. So average power supplied by the source. So average power supplied by the source. So P average source. So P average source will be 1 by 2 Vm Im source cos of theta V at source minus theta I at source. So 1 by 2 Vm source power is voltage is 5 multiplied by the current. So remember, the current is the same throughout the circuit. So current is 1.118 cos of theta V angle is 30 degrees minus 56.57 degrees. So if I am going to multiply it, this value comes out to be approximately equal to 2.5 watts. So this is the power that is supplied by the source. Now, what is now the power average in a resistor? So for that, we again have Vm resistor, Im resistor, cos of theta V resistor minus theta I resistor. So voltage across resistor VR. So VR is basically IR, Ohm's law. I current I know the value of R is 4. So 4I is the voltage and I is the current IM or whatever the current that is flowing. So we just simply say half VM is 4 times I M R, and again this is IM R cos of and theta for both the value of because in this case the voltage and current, the angle of or the current and voltage are in phase, so technically there will be no angle of no phase difference. So again, let me write it theta V minus theta I R over here. So 4 times Im, the value of Im is 1.18 multiply by 1 by 2, 4 into 1.118 cos of the voltage angle. So this angle will be 56.56, so 45.57 degrees here. So we are basically minus 50, same angles from. So this thing comes out to be this multiplied by 1.118 square and my value is approximately again equal to 2.5 watts. So what we have seen from here, so what we have seen is that our source is supplying 2.5 watts of average power, and our resistor is absorbing all the average power, or all the average power that is being supplied by the source, right? So source is supplying 2.5 watts, and our resistor is basically uh, absorbing all this power. So technically, if we apply, so the point is how how we can say that this is the power that is supplied and this is the power that is absorbed. So we can say that with the help of this current convention. So if this current is going out from this positive terminal, so this eventually comes up with a negative sign here. So this will be minus 2.5 watts. So this minus 2.5 watts is basically what determines that the power is supplied. And since the current and voltage, so volt positive terminal is here and the current is entering the positive terminal across the resistor, we can say that the power is absorbed, or the both of the sign for voltage and current are in sync. So we can easily say that yes, this is the power that is absorbed across the resistor. So let's solve another example. So in this example, what it says that we asked tells us to, or it's asked us to say that determine the average power generated by each source and the average power absorbed by each passive element in the circuit. So we have two multiple sources in this circuit. So we have a 4 ohm current source and we have a 60 volt with an angle of 30-degree voltage source. And we have three different components: a resistor, inductor, and a capacitor. So we have technically 5 different elements in the circuit, and we have to find out what is the power that is generated and what is the power that is being absorbed in the circuit. So if you have to solve the circuit, you just simply use the mesh analysis technique. So this is my current I, loop 1, and this is my loop 2. So for loop number 1, we have a current source in the loop, and I1 will be equal to the value of current source. So this will be the value of this. And for loop number 2, what we'll be having for loop 2, we'll be having minus J5 I2 plus 60 angle of 30 degrees, because the current is entering from the positive side, leaving from the negative side, plus minus J10 times I2 minus I1 equals to 0. So this is my equation number 1 for the first loop. This is my equation number 2 for the second loop. Solving equation 1 and 2 simultaneously, we get, or just simply plug in the value of I1 in this equation, we get I2 equals to the value of I2 is 10.58 angle of 10.58 angle of 79.1 degrees amperes approximately. So this is the value of I2 which we have. So we now have both values of I1 and I2. So now just simply, so this is for source 1, source 2, source 3, source 1, 2, 3, 4, and 5. So let's say try to find out the average power across these components. So first of all, let's say across device 2, that is a resistor. So across the device 2, the power absorbed is will be so the power absorbed, let's try to find out. So a power average will be 1 by 2 Vm Im cos of theta v minus theta I. Im across theta 2 is 4 angle of 0, because this is the current that is, or I1 is the current that is flowing here. I1 is the current that is flowing over here, and the voltage across the source will be 20 Vm will be 20 ohms into 4 angle of 0, or the voltage across will be 480 angle of 0. So if you have to find out power average, 1 by 2 Vm, again 80 angle of 0, multiply by Im 4 angle of 0, and the real component of this. If we are going to do the phasor analysis, so eventually we'll get 1 by 2 into 80 into 4, and this comes out to be 160 watts. So this is the power that is being absorbed across this device. Similarly, if we are talking about across device 3, and device 3 is inductor. So if device 3 is an inductor, again the power formula remains the same. The voltage across the inductor Vm across the inductor will be J10. This is omega L into I. I is the current that is flowing is I1 minus I2 that is flowing through the inductor. So J10, I1 is 4 angle of 0 minus I2 is 10.58 angle 79. So 10.58 angle of 79.1 degrees. This is the current. So eventually my Vm will be J10 so my overall current will be so the overall voltage will be something J10 this. So this value, let me write down the exact value. So this value comes out to be 10.58, and we are having this minus 79.1 plus 90 degrees. The angle comes out to be, so Vm will be 10.58 angle of 79 plus 90. So it is something as plus 10.9 degrees. So this is the voltage that is appearing across this and the effective current. So the effective current I is I1 minus I2. So if the effective current, if you have to find out the effective current is 4 minus 10.58 angle of 79.1. So this thing is approximately 10.58 angle of minus 79.1 degrees. So this is the effective current here. So now we have both effective current and voltage. So average power will be half Vm Im cos of theta v minus theta I. So just simply half Vm. So Vm is 10.58 multiplied by 10.58 Im cos of theta v is 10.9 minus and minus 79.1 degrees. So if you are going to do this, this thing comes out to be 90 degrees and this thing is goes to 0. So my average power across this third component is 0 watts. So we have seen that the inductor actually doesn't absorb any active power, or doesn't absorb any power from the source. So now let's see for capacitor, for device 4, that is a capacitor. So for the device 4, what we have current I2 that is flowing across the device 2, and my value of current I2 is 10.58 angle of 79.1 degrees. This is the current that is flowing through a device I2. And my voltage V2 will be minus J5 into I2. So if I'm going to multiply it, minus J5 into I2, what I will be getting, right? Angle of 79.1 multiplied by minus 5J. My voltage value will be 52.9 angle of minus 10.9 degrees volts. So this is the value. So now power average is half Vm Im cos of theta V minus theta I. So again, here what we see that the voltage is magnitude of voltage 52.9 multiplied by the magnitude of current 10.58, cosine of minus 10.9, voltage angle minus 79.1. So we are again here, so this is basically cos of minus 90 degrees, and this is equal to 0. And again, so this comes out to be 0 watts. So we have seen that the power absorbed in a capacitor is also equal to 0, that there is no capacitor, power that has been absorbed by the capacitor. So now let's see for device number 5, that is the voltage source. What is happening across the voltage source? So voltage source, we see that the voltage Vm V of the source is 60 angle of 30 degrees, and the current that is flowing from positive to the negative side, I is I2, and that is 10.58 angle of 79.1 degree. So my average power across that source, P average, is Vm 60 multiplied by 10.58 cos of 30 degrees minus 79.1 degrees. So this value, interestingly, comes out to be, if you're going to find out this value, it is around approximately 207.8 watts. So what we are seeing here is that our device 5, which is a voltage source, is absorbing this much amount of power as well. So actually what now we can say that the source which we have or our current source, which was in our loop number 1, is the one which is actually supplying the power to the source. So let's see what is now the value. So now we know that the law of conservation of power. So law of conservation of power says that P1 plus P2 plus P3 plus P4 plus P5 must be equal to 0. The overall power must be conserved in the circuit. So we do not have the value of P1, but we have the value of P2. The value of P2, we have calculated it to be 160 watts. So P2 is 160 watts plus 0 watts for P3, 0 watts for P4, and 207.8 watts for device number 5. So overall, we can say that P1 is minus 160 plus 207.8 So P1 is approximately minus 336.78 watts. So this is the value of power that is being supplied. So this is, since it is in the minus sign, this is the value that is being supplied by the current source. So this is how we actually find out how much power that is being supplied and how much power that is being absorbed by a circuit in a AC, in an AC circuit. So thank you very much for listening. We'll start our next lecture for maximum average power transfer for the next time. So thank you.